All right, guys. So first thing first, I think what we're going to try to get you to see the thermodynamic stuff, and we're gonna have like an hour, a little less than that, to talk about this one is we're gonna talk about thermodynamic system, and I'm gonna explain a little bit about why do we need this, why do we need physics at all, right? So I'm gonna talk about what is uh, the stuff that we keep talking about, thermodynamics. So I'm going to propose to you the thermodynamic systems. What are those? Okay. And the key that get into this picture is about temperature. So I'm going to speak about the what is actually temperature. Okay. And once we get that, we're going to get this one out of the way is the Zeroth Law of thermodynamics. And you're probably wondering why there is like law number 0. And then you will see that this is physics people only that do this kind of thing. All right. So let's get to that. And then we'll see some consequence of that in thermal expansion. And we'll see how far can we go. Okay. First thing first, what is thermodynamic system? Let's think about this a little bit because this is like first time we see each other and just try to draw you into these topics. And I want you to get some motivation. So I want to have you guys feel like what is going on here. So what I'm going to ask you is this, and it's like, maybe it sounds like simple, but I'm not sure what is your answer. How many oxygen molecules in your room right now? Approximately, of course, you don't know exactly, but at least you should be able to get the order of magnitude, roughly 10 million and stuff. That's what it means. I'm saying order of magnitude. What do you guys think? How many oxygen molecules floating around or sort of like around your room at this point?
10 billion.
10 what? Billion?
Billion. Yeah.
Million.
Yeah.
So it's 10 and million. That's 10 to the 6 molecules. All right. Anybody giving higher? It's like we're doing an auction here. All right. Anybody? 10 million right now. 10 million right now. Anybody? 20 million, 30 million. All right. Anybody else? But thank you for the answer though. That's appreciated. That's make it like that's you already made my day here. All right. So 10 million. If there are no further suggestions, have you heard of Avogadro number? Maybe in chemistry? Yeah, mole. Yeah, that's very good. So you related to that. What is 1 mole, guys? Sort of remember this? Let's just give an order of magnitude. Yeah, oh, very good. That's very close to exact. It's 6.02 times 10 to the 23rd. So that's approximate. Whoa. So think about this. From million to this is like what? Crazy, right? It's like million is almost another million there. So there's a reason for the mole unit because that's how much you have to deal with in chemistry or in physics, of course. So that's what it is. You have to deal with every day. And that the formula that I want to propose to you guys today is you familiar with this. And that number of mole is waiting for you in this equation right here, right? And this is a number of mole. So that means every time you talk about the gas system or even the liquid system, and then when you talk about the microscopic level, you talk about the molecules, then you usually don't want to talk about the number of molecules because it's big. That's why you invent the unit of mole. And that leads you to think, if you look around you, you can probably put in some, maybe you can say, hey, I know, oh, what is going on here? I know some, whoa, I cannot write on this. All right, that's bad. Okay, right here, it's Android. Okay, so you might know the pressure, you know the volume, you know the temperature of your room and other stuff, you know the constant R here. You should be able to approximate the amount of molecules in your room. Even though the formula is not perfect, we will discuss more on this. It's an ideal gas and other stuff. Then you might say about Ajahn, oxygen molecule is not ideal. It's not like monatomic molecules and all this stuff. Don't worry about it. I'm just going to get an idea that you're going to have to deal with this big of a number, 10 to, let's say 10 to the 20th. Think of it that way. All right, so that's give you a good start, right? So a million is still small in comparison to a mole. So you need like million stuff like that. That's about 10 moles. So second question. If I want you guys to give me the energy, the kinetic energy of oxygen molecules in your room, what will be the way that you can calculate that? Come on. I want to know. All right, you guys are Ajahn, that's no big deal. I know 1/2 mv squared. Yeah. All right, that's an answer. I need to know the temperature. Very good. Very good. You're already ahead of the curve right here. Very good. So if you think of it like, okay, Ajahn, from Newtonian physics, the kinetic energy is 1/2 mv squared. And let's say we ignore other stuff. Let's talk about the movements alone. So the way that you can calculate the net kinetic energy of this molecule is a sigma k. You just sum them up. Done. Just no big deal. But the problem now is how can you sum the numbers that has 10 to the 23? Even you have like a supercomputer, you still have problem of detecting that velocity, right? Because to be able to know that speed, you have to somehow set up a sensor or something like that. And when the oxygen molecule just drive past by, you detect the speed and then you do the 1/2 mv squared and sum them up. And every time that you want to calculate it, you'll be able to capture all those movements, put it in this equation, sum them up. That's impossible to do manually. Well, I can say impossible because you won't be able to do it in real time because those molecules will knock each other out, change the speed all the time, change directions, velocity change. You have to recalculate 1/2 mv squared again, and then you have to do the summation all over again every second, every split second. So that isn't impossible for you to do. So the question is, can you still answer this question though? If I want to know the total kinetic energy of the molecules in the room. Can we answer these questions? We cannot do it by hand right now. The answer is yes. And that is thermodynamic system. It's just weird. I just feel it. Yeah. So the thing is, the thermodynamic system comes into play when you are dealing with the system that turns out to have something in the macroscopic world to be like a neat looking system or this stuff. But when you want to dive into a detail in a microscopic level, well, you try to link it to like Newtonian physics and other stuff, but then you cannot do the connections, even though then you know exactly how they are connected, but you cannot do it by hands. So that's why we need another way to approach this sort of macroscopic analysis, and that is a thermodynamics. That's a subject that we are studying. And it turns out under this thermodynamics, you have a thermodynamic system. This can answer your question, my question, sorry. I can answer my own question. It turns out this is under, just your friends told us, turns out to be temperature, guys. Believe it or not. When you measure the temperature of your room, that is the measurement of the total kinetic energy of the gas molecule in that room. Given that, I mean, you don't have any complexity, think of it like you have only single kind of gas or other stuff. But anyway, that's the rough idea. Temperature can represent the whole crazy stuff that's going on in a microscopic level. But in a macroscopic level, it's neat. T, just give me temperature. You're done. That is the reason why the temperature is baked into the thermodynamic system very closely, because that is a one kind of variable that is a macroscopic variable that can describe your system. Okay, sounds like a good plan here. Okay, so that means you want to be able to describe the system, and you still want to know the dynamics. That's the key. But it's not the same kind of dynamics that you did with the Newtonian physics. It's the dynamics that involve thermal. So when you talk about the thermal, that's why you need to talk about the temperature. And then when you talk about the temperature, then there will be some stuff going on. That is the dynamic that is responsible by the temperature difference. And the temperature now link between the macro to the micro stuff that we have over here. And once we understand thermodynamics, then you can throw away all those microscopic questions. So you shouldn't ask anymore, but Ajahn, can you give me the total kinetic energy of oxygen molecule? You don't ask this kind of question anymore. You just give me, hey, what's the temperature right now? Like, 25 degrees Celsius, and then you be done with. Okay, sounds like a good plan. All right, see, it's kind of fun, yeah? Okay, so temperature, that's the thing. And the way that you can measure the temperature is, of course, use thermometer, okay? But the thermometer, it turns out, is nothing more than just is a comparison. When you want to do a thermometer, this is what it is. So you have some physical parameters or something. For example, like this one, you have like a mercury thermometer. You just want to measure the expansion of the mercury when the temperature changes or the stuff. So to be able to measure the thermometer, the temperature of, for example, here the water, you just take the thermometer and dip it into it. So what it is you want them to be in contact. That's the key. Okay, and because before, the temperature of the thermometer probably going to be different from the water. Once they are in thermal contact, once they are in contact, the temperature difference will act something on it. So that's why this kind of contact is being mentioned as thermal contact, because it's a contact between two things that have different temperature level. Sounds like a good plan? And this is the reason why you haven't learned about this thing in Newtonian physics. When you talk about mechanics, you want to push a block, a block or a mass or whatever. You never ask about that temperature. See that? Don't care. I don't care how hot of the day you're doing, because you are not looking at the aspect of the thermal stuff. You still just want the mechanics out of it. But right now, we're going to talk about the thermal stuff. So when they are put two things that have different temperatures in contact, you're doing a thermal contact. And there will be some dynamics going on through this boundary. Okay, all right. And spoiler alert, that's what we're going to talk about as heat. There is some flow of stuff. All right, but anyway, that's the story of latest. All right, we're going to talk about that. So in general, once you dip your thermometer into stuff that you want to make a measurement, and you have to wait a little bit for it to settle, and then you read the scale and all this stuff. So when you want to wait until everything settle down, that's when it reaches thermal equilibrium. Sounds good? All right. So that's what it is. Like same thing over here. You turn on the air conditioner. At first, the room is hot. The air conditioner is working its thing. And then you just have to wait for a while for the temperature to reach some equilibrium temperature. And that's when everything is sort of like, think of it like in equilibrium, temperature wise. Yeah, and the temperature, everything is good. I mean, it takes energy out from the room, exchange all this stuff, and keep the room at some specific temperature. So that's the idea. So thermal equilibrium is when the temperature is stopped changing. So when you're doing all this stuff, it leads you to a very simple zeroth law of thermodynamics. It says, if an object A and B are separated, all right, are separately in equilibrium with the third one, let's name it object C, is guaranteed that A and B must be in equilibrium as well when they are in thermal contact with each other. Sounds good? So actually the zeroth law of thermodynamics is related directly to the thermometer. If you dip a thermometer in object A, it reads 22.5. Dip it in object B, it also reads 22.5. Then you say, if you put A and B in contact, nothing happens. I mean, nothing happened means they're already in equilibrium. Okay. And that's it. I don't know. It's a little bit of history. Then they already defined the first law, second law, and third law before this law, and they just realized that hey, this law is like a fundamental of everything. So they say, I don't know where to put it. Let's call it a zeroth law of thermodynamics. Yeah, this is physicists only characters that they can add like a zeroth law of thermodynamics. Yeah, that's kind of weird. All right, but that's what it is. Okay, just let it go for the zeroth law because it's so common sense that you should be able to understand this one using just your everyday experience and everything. Okay, sounds good. All right, now talk briefly about the scaling. So you have Celsius in Thailand. We use that Celsius stuff, and many countries use Celsius. In US, we still use Fahrenheit. I think maybe that's the only country left that is still using Fahrenheit. But in physics, though, we use absolute temperature scale. The reason is, first of all, we found out this absolute temperature later, just way after we already defined Celsius scale. The Celsius scale is based on water. So that's why they take the vaporization temperature, 100 Celsius, they call it 100. And then at the freezing point, they call it 0. So the scaling of the Celsius coming from ice turned into vapor. So that's 0 to 100. All right. So that's reference to water. But later, of course, we learned that there is an absolute like things that actually has to follow no matter what kind of material or substances you are talking about, not only water. And that's why we create absolute temperature scale. Okay. And then we'll talk more about this in a little bit. And don't worry about this setting over here. I think chemist people will like this kind of thing. But for us, well, I think it's better for us to talk about what is it? What is the absolute temperature? Right. And don't worry too much about the experimental setup over here to try to get to the absolute temperature scale. So my question is this. All right. So you know the scaling, everything is fine. You can convert between Celsius and Kelvin, the absolute temperature, no problem. Okay. Here comes the question. If I have an object, and imagine that this object is like a single object in the universe, right? Black. Universe is like completely empty. There's nothing there. And this is the only single object in the universe. And somehow I give it something by burning it up, which is, Ajahn, that's kind of like you cannot sort of get the fire to ignite in the vacuum, you know. Okay, let's say I shine the laser light on it, something like that, beep, something like that. So think of it like I want to heat it up. All right, I want to give it some energy by, all right, light the fire, which is impossible. All right, I'll shine the laser light on it. Okay, good. What happened to this object? What do you guys think? At first, it's just a single object in the universe. And suddenly, somebody gave it some energy. And this one is through light. Yeah, it's getting hotter. Okay, very good. What does it mean by hotter? It's a single object. What do you think? It's like a single, think of it like electron. Yeah, like electron, proton, some super fundamental particle. What does it mean by hotter? It's getting hot. But I'm the only single object right here. How can I get hot?
Oops.
Oops. oh, yeah, there's an increase in entropy. Now that's complicated. What does it mean? Entropy. More energy, of course. Yeah, we'll just give them energy. Very good, very good. We're getting there. Just move. Yeah, very good. All right, so you get to the right direction. So the key is once you get the energy, how this particle will do with that energy that it received. Because it is the only particle in the universe. There's nothing else it can do. The only thing that it can do is just move. Give it some velocity. You guys with me? Keep it because it's green. All right, think of it. When you say you want to keep it, it has no structure in it. It's such like a super simple particle. It has no backpack. It has no hands. It has no pockets. There's no way for it to keep it. Keep it where? See, it's a simple particle and it's just a single object. So that's why when it receives the energy, the only thing that it can do is move. It has to move. With me, guys? And that's give it kinetic energy. And we just talked about this. If you have any kinetic energy in the thermodynamics world, eventually it will lead you to temperature. Now you get me what I'm trying to say? That means at the point where this object does not move, it means the K is zero, velocity is zero. That's where the temperature is zero. Got it? That is a simple explanation of absolute zero. Is when nothing is moving. That's why in this experiment right here, if you try to reduce the temperature, of course, no matter what kind of gas, will eventually reach the same single point, because that is the point where all of the molecules or all of the atoms in the gas stop moving. See, that's absolute right here, even though it's unreachable. That's bad. That is a twist right there. Hak mum. All right, so that's sort of like a weird ending over here. Even though we know in theory that the zero absolute temperature means nothing moving, nothing is moving, but it turns out the zero absolute temperature is the temperature that is unreachable in this universe. And that turns out to be the third law of thermodynamics. Nothing is at 0 Kelvin. The Kelvin is the unit of absolute temperature scale. Okay, sounds good? All right. And the reason for this, there's so many ways that we can explain this, but maybe the easiest one is maybe quantum mechanics here, that nothing is actually stop moving. It's against the rule, something like that. So when you cannot pinpoint that a particle stop moving, then that means it must move somehow. When it moves somehow, it must have some temperature in it because it has some kinetic energy in it. That's what it is. All right, guys. So I hope this gives you a grand sort of overview of what the absolute temperature is. It's just the point where nothing is moving. So the way that you can reduce the temperature of the gas, turns out you do whatever it takes to stop their movement. So from now on, you don't need just only a refrigerator, because the refrigerator, you just use something colder and then just pump out the energy or the stuff. We will learn more about the refrigerator, internal working stuff later. But the idea is you don't have to use refrigerator all the time. You can use laser light to stop particle. For example, I can shine the laser beam in all direction, front, back, left, right, top, down, onto a single particle, sort of like try to nurture that, sort of like, hey, don't go anywhere. And that particle stop moving around. And that's where the temperature start to drop very close to 0 Kelvin. Okay, but you can get only so close, like maybe nano Kelvin, or maybe sub nano Kelvin, 10 to the negative 10, 10 to the negative 11 Kelvin, but you're never going to get to 0. Yeah. All right. And what happened next? That's it depends on what you want to study. When you want to get down to that, okay, the thing is, when you study something in maybe chemistry and physics and biology, and then when you start talking about the theory, everything we assume that it happens at the time that there's no fluctuation at all. So that's mean you assume 0 K. For example, when you have some, let's say radiation, for example, when you look at the hydrogen atoms, when you do spectrum analysis, there is like a line. So when the electron change the energy level, it's give out some light or the stuff. That we assume that the hydrogen atoms is sitting at a very close to 0 K. That is like in a pristine, perfect scenario. But when you try to do an experiment in a room temperature, the hydrogen atoms, turns out the nucleus is not going to be super steady. The electron is still moving around with some extra energy due to the temperature and stuff. So there'll be some fluctuation on it. So when you want to cool things down to very close to 0 K, sometimes you want to just to confirm your theory, because your theory is assumed that there's no fluctuation due to the temperature, something like that. Okay, sounds like a like a good connections there. Okay. All right. So in our world, of course, we are living, let's say, about maybe 30 degrees Celsius. So the way that you can convert this to Kelvin is just add 273. Actually, you can add 0.15 if you want, but I think 273 for us, I think that's good enough. So you just add that to it. It will give you through to about 303 Kelvin. So we are living in the world that has the temperature around 300 Kelvin right now at this point. Okay, so that's the absolute temperature scale that we are living in. Okay, all right, your body temperature will be around 310 Kelvin, maybe, thanks to the sun, yeah, and also thanks to the ozone layer and all the carbon dioxide, all the greenhouse effects in a little bit, and yeah, keep us warm and away from radiation and all this stuff. Yeah. All right. Very good. Now we still don't know where we are. I mean, where we're from anyway. So, okay. So Fahrenheit, I think we can skip it a little bit. However, if I think that's a kind of good to know, it turns out that 40 Fahrenheit negative, that's below, is the same reading when it's in the Celsius scale. So when you are at 40 below, it's the same temperature, Fahrenheit and Celsius scale right there. All right. And if you want to convert between them, you can use this formula or just do the Google, punch in the Google and then do the conversion for you. All right. That's good. All right, here we go. So once we kind of get to the idea of what the temperature is and how is the temperatures connected to the kinetic energy of the system, here comes the first property that we're going to learn here. And then I think that's the end of today's lecture here. I'm just going to talk about the one single properties that is so easy to understand and is connect directly to it is the thermal expansion, guys. Now you guys sort of going to be able to understand this one easily. Think of it this way. If you guys sort of come into a room and let's say jam packed, like shoulder to shoulder packed, okay? And then you're sitting there and suddenly I turn off the air conditioner. Right. So the room will start to get hot a little bit because you guys are in the room. You guys are sort of like radiating all this stuff, right? So after a while, it will get annoying a little bit because you sort of like feel uncomfortable. And then you seem like, hey, can you move away from me a little bit? It's kind of getting hot. So the way that you sort of duk dik a little bit here, that's when your temperature is rising. That is sort of like analogy to higher temperature mean more movement. Okay, so the key to take home today is higher temperature mean higher kinetic energy. For a simple particle, it means it's just move. For a complicated structure like this one, all right, it cannot just run, right? Because it sort of gets stuck into like a structure or something. So higher temperature means more movement. It's more movement. I mean, no matter what, you need some kinetic energy. So what you have over here is, so when the room starts to get hotter and hotter, you just move more and more because you're sort of annoyed with the hot room and other stuff. So your elbow will start to knock with your friend's elbow and that's it. On average, you guys try to stay separated. And that's your thermal expansion. I don't know if this is a good analogy or not, but anyway, that's what it is. So when I say thermal expansion means when you raise the temperature of the substance, the energy of molecules getting higher, the movement will be more. So the average distance between molecules will start to increase. But everything that happens in the microscopic scale, eventually, once you zoom it out, look at like a big picture over here, then you will get an expansion. Okay, you guys with me? All right. So even though you talk about here, you might say about Ajahn, the whole thing, this is like in the nanometer scale. All right. And then you elbow to elbow, maybe like an angstrom stuff. But then you have Avogadro numbers of this. So when the shaky stuff going on, then you can measure the expansion maybe in millimeter in a macroscopic world. That's possible. And that's what we call thermal expansion. Okay, sounds cool? All right, so that's what it is. So how are we going to be able to model this thermal expansion? And as you can see, when I say model, because you know what is going on in the microscopic world, but you're not going to be able to do that from the microscopic to macroscopic in full detail, you probably have to try to explain this thermal expansion using something simple. And the concept is so easy. I'll show you what it is. Start with this. You have like a substance in the form of like a rectangular bars over here, and then you heat it up. And you can notice that it's going to expand. Everyone sort of seen this. You might be able to measure that length extensions right there. So it's say, oh, John, it's getting longer. And then you'd say, hey, there is some relationship between the length that is getting longer, the change of that length. It depends on your temperature rises. Yeah. So that's good. But okay. The harder that you can take this, I mean, you increase the temperature, the bigger that delta L. That's all right. So at least you know that the delta L should proportional directly to the change in the temperature. That's first thing. And the second thing is, how big is this change? It depends on how already the substance started out. I mean, if you started out with like 1 meter and you compare this with like 100 meter, of course, the 100 meter will extend very more obvious than the just 1 meter length substance, something like that. So it depends on what is the initial length of that stuff that you are looking at. And the last one is, maybe that's what your friends comment. How strong is thermal expansion? Exactly. That's very good. So you have to say what is the strength, using that his words over here. What is how good of this substance can expand or react to the change of the temperature. So we must have something to help with this. So that's why you need to define something we call the coefficients of linear expansion. So we're going to name this the alpha right here. Cool. Oops, sorry. The alpha. All right. So this alpha, the coefficients over here will tell you how good or how bad this substance can expand with respect to the temperature change. And as you can see, the reason that try to get to this in this form here is just make this equation simple to treat. Is a linear equation. Everything is in the first order. It depends on the temperature change. It depends on the initial length, and you have some coefficient to deal with the alpha, and that's it. Okay, cool. All right. So the alpha for a well-known substances are listed. Like some examples here is in this table right here. See, you can see that the aluminum, brass, copper, they are pretty much about the same. I mean, very close, same order of magnitude. Glass is not very good at expanding. It's only 3. Okay. Concrete. This is good stuff. If you notice, concrete and steel, the number are very close. And now you see the reason why. Because every time you do like a skyscraper, building a buildings, constructions, everything, you have like steel reinforced concrete, right? And of course, that means in that structure, you have concrete and steel in the same structure. So during the daytime, they get the same amount of heat from the sun and all that stuff. So they're supposed to expand and contract at the same rate. Otherwise, then you're going to destroy some concrete. Maybe, some steel in there just pop up and all this stuff. It crack the concrete and all this stuff. So that's why from the engineering purposes, you want the steel and concrete to have the same coefficient of expansion. That's it has to be. Otherwise, then they're going to have some problem right there. Okay. All right. And this is like a well-known sort of like a image that showcase what happens when you didn't take into account the expansion from, in this case, maybe steel or something like that. So this is what happened. But I'm still wondering about this picture all the time. I cannot get my head around this. It's just like, why can they, how can they complete the whole project without facing this problem? Because they have like the train, everything running already. And I don't know, the railway just get worse, get bad, or I don't know what happened here. It should already show up like this before starting the operation. I don't know why. Or maybe they have done this in some weird temperature and then there's a global warming and other stuff. Who knows? All right, but that's what it is. All right, and the cracking on the surface of the land and other stuff that's happened when the soil on the floor just expands and then it just sort of fight each other and it's just buckling up. All right. Okay, maybe they finish it in winter. Yeah, that's what I thought too. They did it in winter and then it's just getting bad in summer. That's possible. But I don't know how fast they can construct that whole thing. All right, but that's still a question for me. Okay, all right, so this is good. So it's so easy to understand. This is like a simple first order equation over here. But then you probably wondering, well, Adan, wait a second. Why you care only about the length? Why don't you care about the height? And what about the depth and everything else here? Like you still have two more dimensions to think about. Yes, that is very good. That is a good question. I asked it myself. So yeah, the reason for this, I just want to showcase that this is when you only consider a single dimension of an object. You want to know what is going on with the length. But in reality, you can apply this equation in all dimensions. The height, the depth, they all follow this kind of equation. So it turns out you can talk about the volume change instead of just the length change. So you can turn that delta V, turn that delta L into a delta volume, the change of the volume. Of course, the concept stays the same. It's still related to how far you change the temperature. So it still linearly depends on the delta T. And it depends on what is your initial volume. That's still fine. And you can come up with another coefficient, and then you can call this coefficient of the volume expansion. One thing that's nice about this one is the equation looks exactly the same. And here comes the question, why? Why, Ajahn? Why the equation for one dimension is exactly the same as the equation for the three-dimensional change? And the answer is right here. This is the mathematics of the day. All right, no extra charge right here. Okay, I'm gonna show you this just for fun. Don't worry about this one. There will be no proof thing in the exam or stuff. But this is good to know, especially for those that comes from like computer science people. I think you guys do this all the time. I'll show you what it is. Here we go. So talk about volume. Volume is the length, the width, the height. You multiply them, correct? Good. Everyone agree. Now, I raise the temperature. So that means if I start at initial temperature T naught and I say, hey, I increase the temperature by delta T, everyone know what should be the delta L, right? The change of the length is going to be, but Ajahn, that's no big deal. You just apply the equation there. That's your delta L. So that means the new length is going to be the original length L plus the delta L. You guys with me so far? Very good. Then I do the same thing for the width and the height because we said they follow the same kind of equation. So original width is W. The delta width is going to be the alpha, original width, and the delta T using the same equation, but then just change L to W. Same thing happens to the edge. Original height, alpha H delta T. Perfect. All right. Very good. It's a cubic equation, of course. Yeah. So what I can see is now I can pull a common factor over here. That's a 2L over here. I can pull it out. So it stopped right there. W, pull it out, place it there. H, pull it out, put it there. And now they have common factor of 1 plus alpha delta T cubed. Question, where does the cube go? Where does the cube go in the volume change? Wow. The answer is this. This equation over here is not a law. It's just a model trying to explain the thermal expansion. So add to it, it has some approximation to it. So don't take this equation too seriously. It's just trying to make your life easy in the sense that, hey, I'm going to show you the equation that is in the first order. I don't want to do any square. I don't want to do any cubes. I don't want to do anything. I just want to make like everything linear. How can I make linear of this stuff? I have to linearize this cubic function right here. Yeah, when a scientist was like, yeah, close enough. Yeah, exactly. I agree. Yeah, science is just say, hey, this is good. Yeah, And in real life, then you do some engineering around this thing and then it should work. So here we go. You guys, computer people, you should know this, I think. Yeah. I hope you agree with me. Have you seen this before? 1 plus x to the nth power is approximately 1 plus nx. Have you seen this? Yes. That's called linearization in the way that, okay, for those of you that still confused, I'll show you this just for fun. This is just for fun. And see like, hey, this is just seeing each other first time. 1 plus x squared. This is a complete square. Everyone knows how to do this. That's good. Cube is still doable. So you see 1 plus 3x plus 3x squared plus x cubed, yeah? I think to the 4th powers, you guys still be able to do it, I think. So it's 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th, on and on. All right, you can still using whatever formula, whatever that you have done before. But then here comes the kicker. What if x is small? Yeah, when x is small, not only less than 1, but it's like small. Let's say maybe 0.1 or even 1%, 0.01. So if you have x to be very small, you can see that when you square that small number, for example, let's give you an example of 0.01, for example. That's already in the 2nd digit, right? So when you square this is going to be in the 4th digit terms. When you cube it, it's going to go all the way down to the 6th digit, on and on. So you say, hey, forget about it. It's too much calculation. It doesn't worth my CPU time and everything. Just linearize it. I'm just going to keep all the way up to only this term right here. All right. And that's it. So that's why, hey, to the 1st order, that's what they say in the textbook in general. Up to the 1st order, that whatever power, you can approximate it to be just 1 plus nx. And actually this one allow you to, I mean, this is just for fun. Every time you see like 1, okay, here we are. 1.01 cube. I say cube, I wrote 4. Cube, right? This. If you don't care so much about fine detail, I can say, hey guys, it's approximately 1.03. I'm sure. With me? Because with 1.01, that 0.01, that's your x. And all I need to do is just multiply it by 3. I know it's going to be, I'm good up to the 2nd digit. I'm sure I'm right. But if you want to know more, then you just do it yourself, stuff like that. So that's why, come back to our business over here, I can approximate this to be, hey, just 3 alpha delta t. All right, and that's good. What is good? When I say it's good, because I can expand the whole thing out again. The LWH is just your original volume. Very good. That LWH multiplied by 3 alpha delta t is in a very good form. That 3 alpha over here, that is in the position of the beta. And that's it, guys. You can see the connection between the alpha and the beta. It turns out the volume expansion coefficient is just 3 times the alpha. Given that the expansion in length, width, height, having the same coefficient of alpha. Okay, and when I say that, that's what it means by isotropic material. Okay, you guys with me? I think I throw in a lot of like technical terminology in here, but I hope you understand what this is. When I say isotropic, it means everything happens in the same amount in all directions. In the x, y, z coordinates, it's an x direction, y direction, z direction, everything expands in the same way, same alpha. If that is the case, it's the beta is going to be equal to 3 alpha. That's isotropic material. And you're probably wondering about, Jan, what about non-isotropic material? Think of polymer. When you have a polymer material, it's like a spaghetti-like. So you can see that the expansion in one direction might not be the same as the one that's perpendicular to the spaghetti axis, for example. right? And then today you have like crazy material that can expand in one direction better than the other. That is a non-isotropic material. But for the material like we are studying, like metal, it looks so nice and clean. Like you have like a piece of aluminum, of course, you can flip around, you cannot stay. I mean, they all look the same in all directions. Like, so that's why metal can be treated as an isotropic material. So this formula looks so good. All right, beta equal to 3 alpha. All right, and this is the connections to all of the stuff that we are introducing right now. Okay, sounds like good sort of introducing myself topics. All right, so this is what it is in terms of, hey, first, this is just a model that has an approximation in it. It's only trying to describe the thermal expansion. So this is not a law. This is like a warm-up stuff. All right. This is not like sigma F equal to MA or PV equal to nRT. No, this is just human approximation. So what about material with thermal shape memory? Yeah, see, that's crazy stuff, because when you say thermal shape memory, it means it has a rigid structure at one particular temperature. So that means every time that you try to change the temperature, it changes the shape. But then if you can bring that back to the same temperature, then it will come back to the original shape. Or you might have to erase some memory first. For example, you might have to warm it up until everything sort of like, hey, you forget everything go crazy again, and then it cool it back down. And once it reached that original temperature, then it will just come back to the original structure. All right, so there's so many material technology that you can build into this, and everything just depends on how you design your microscopic level molecules. Yeah, that's I mean, it's crazy stuff right there. Yep. Okay, but they're all related to temperature though, because that's how you drive the dynamics of it. Okay, that's why every time, most of the time, it's either mechanics or thermal now. If mechanics, then you have to, force on it, apply some force on it. Or thermal, you just have to warm it up, cool it down, sort of like, hey, bake on it or something like that. Put it in microwave or something. All right, cool. All right, so this is just another thing that I just want to add, like, it's like a cherry on top over here. I can approach this whole thing without doing this mathematical approximation. I can do this through calculus as well if I like. All right, but this one just for fun, because when things go so small, when I say so small, it's a differential change. Let me put like a highlight over here. When you say dl instead of the delta L. So when things change so super small, everything approaching zero, those approximation will come in to be very, very, very close to perfect. Because even here, I assume that x to be like 0.01. But if x is like 0.0000000, then your first order approximation will be so close to exact already. So this is what it is. So it's even nicer to use calculus over here, because I can do this. I say, hey, Dan, what is the change of the volume? Just a tiny bit. I call it dV, differential change of the volume, super small change. And then say, hey, Dan, I want to change this to link to the change of the length. And I know the volume initially is just L cubed, starts simple, which is a cubic stuff. So length cubed. You want to know the change with respect to the change in the length. What do? You do the derivative. dV by dL is just 3L squared. And I just rewrite everything in terms of the differential. Why not? You guys with me? Already? So if you start from the dV, I can do the chain rule. You can think of it that way. It's just dV by dL times the dL. But the dV by dL is just always 3L squared. Just plug it in here. That's it. So that means every time you know what is a tiny change of the length, you should be able to calculate the tiny change of the volume by multiply by the 3L squared. But then we just said the change of the length. Oh, let me use this bright color here. Taking from the expression from the linear expansion, is going to be alpha L dt. You guys with me? I'm writing like this because this even better than the delta. It used to be alpha L delta T, but now I make everything to happen infinitesimal and small change. Super, super duper, super small change. So that's an alpha L dt. So I can turn this dl into alpha L dt. I'm just going to leave that alpha L to the front term. Take the 3 alpha, L square, meet with the L, you get L cubed over here. But the L cubed, which is your original V, you get back to the same expression. But of course, if you take this expression over here, it works even better because it's the differential change of the volume when the temperature changes by tiny bit. It's going to expand by beta V dt. But anyway, the point is you get the final form of the formula. Perfectly fine. Okay. And from the understanding of these two, I think you're done. What happens if you have only two-dimensional stuff? Like you have a sheet of metal. What would be the area change? The expansion of the area? Ajahn, I can guess it's going to be 2 alpha. Okay. So the conclusion I want you to get today is just this. Once you understand it, you know that it's just an approximation. You linearize everything. Change of the length is alpha L delta T. Change of the area to alpha A dt delta T. Change of the volume, 3 alpha volume delta T with linearization built into it. Sounds like a good plan. All right, guys. So with that, there is a table for the coefficient of volume expansion for you guys. And I mean, because we know that mostly the volume change works well with the liquid or gas stuff. So that's why this table listed the substance in gas and liquid phase. In the solid phase, we can multiply alpha by 3 to get the beta. So that's what it is. Okay, and one quick application of this one, you probably haven't seen this anymore, except you still have super old air conditioner at home or some temperature controller that's pretty old. They use this thermal expansion properties to control the temperature because like this, you see that you have a steel and brass piece. It's called bimetallic. So you use metal, 2 types that has a different expansion coefficient. So when temperature is raised, then the brass expands more than steel. So this bimetallic strip will bend. And when it bends, then you can sort of stick this bending bimetallic to the switch. So you can use it to control temperature. When it's hot, you just turn on. When it's cold, you shut it down, on and on. All right. So this one is called thermostat. So it's the one that you can use to control, turn on and off electric stuff back in the day. But now you use electronics now, right? You don't use this kind of like big mechanical things anymore. Okay. All right, guys. So I think that's conclude the whole thing. All right. And I'm going to end today's lecture with just this exception. And then we'll see you guys on Wednesday and we'll do some exercises. Sounds like a good plan. All right. Last piece of the slide is this. There's always some exception because you have already seen that everything comes from microscopic structure. Water is nasty. So it doesn't follow this whole thing at all. The water has the highest density at around 4 degrees Celsius. So too bad. Water is too complicated. So if you start at water at 4 degrees, no matter you warm it up or cool it down, it's going to expand no matter what. Okay. So conclusion, take this equation just lightly. Don't take it too seriously. Right? It's just a modeling, linearized approximation. Everything built into this one just to get you to explain thermal expansion in an easy form. Okay, sounds good. All right, guys. So I think that is it for today. All right. And I'll see you guys again on Wednesday at 8. Yeah, sounds good. All right. And I'll post the Zoom link on the Google Classroom. Sounds good. All right, guys. Have a good day. I'll see you guys on Wednesday. Take care. Bye-bye.